Okay. So I got a question, 6-1, number 84. Is it all about truck wheels?
Yes.
Okay. So truck with 40-inch diameter wheels. So again, this is number 84. And 6-1. Is traveling at 50. Oh, okay. So we haven't talked about it. So, all right. Let me hold off on that. We haven't talked about angular speed yet. Right? So little details like angular speed and stuff like that, we definitely haven't gotten. Yesterday was just pure concept. So I'm going to put this right here. We'll look at later. Yeah.
Do you have any other worksheets you passed out?
Oh, yeah. Let's see, who else needs that?
I lost my grid.
Oh, yeah. Anybody else need that?
Oh, I guess not really.
Hold on to that one.
I'll try.
Come back tomorrow.
I post that thing on the website.
We should come back tomorrow. There's tomorrow.
All right. Yeah.
I want to how to find the reference number. I think 5.1 number 36.
Yes, so that was the earlier thing. So we gotta cover that. We covered it a little bit, but I want to make it more of a official kind of a process. So anything else? I mean, so they're all like, I don't know, dude. So let's get back in it. Let me review a little bit of what we did yesterday, not the whole damn thing. See if I could do this very quickly. So the rough idea for this starts with what's called the unit circle. It's got a radius of 1, which is why it's called the unit circle. And any point on this thing has got to follow this equation. So that's where all these points kind of come from. Now the minute I draw in a specific angle, that kind of defines this triangle.
You know what's called theta?
Say again? Alright.
The angle.
It's called theta.
Oh yeah, this symbol is Greek letter theta. So if you're going any further in mathematics, that's just going to become second language. You're going to look at that and your brain's going to say theta. It's just going to be a word for you. So, and of course, these go together. The definition of a circle actually comes from a triangle. All these triangles make this circle. They all have to be the same distance away. So that's really just the distance formula, which is Pythagorean theorem. Right, so it all kind of comes back on itself. Yeah. So, if I'm at a certain angle where, let's say, the x piece is root 2 over 2. Some of you guys know what the other half is, but how do you show what the other half is? Just plug it in, right? Just plug it in. So if you plug that in, so some of the homework is probably going to say verify that this point lays on the unit circle. That just means plug them in and show that it equals 1. So what do you get when you square root 2 over 2?
2.5.
2/4, so 1/2. So 1 minus a half is 1/2, and then the square root of 1/2 is 1 over root 2. And if you rationalize that, what do you get?
Root 2.
Root 2 over 2. Yeah. So, and of course that makes sense. That means I'm at what angle? 45 degrees, otherwise known as how many radians?
Brad 4.
Pi over 4. I like it. So what the hell is that? So, very quick review about radians and degrees. So the cool thing about radians that I want you to remember is it's actual measurement. I tried to make this a big deal yesterday. Theta degrees are just completely made up. They could have been any number. We just picked 360 because 360 is easy to cut up, and that's one thing you want to do with a circle is cut it up. Radians are truly, if I have a circle of radius 1, if I go this far, if I go far enough to cover, I don't know what it says, one radius worth, so here's the radius of 1, so if I go far enough to go 1, so this is 1 foot, if I walk 1 foot here, that angle I just went through is 1 radian. And that's that animation I showed you, where they took the radius and they curved it. So if you do walk a perimeter of 1 foot, and you've got a nice circle that you walk around, you've actually just gone through an angle of 1 radian. That's crazy. Yes, sir?
So then would 1 radian, would that be like pi over 4 to pi over 3?
Oh, you talking about where is it?
Yeah.
Yeah, it's definitely, it's in between those 11. Because now let's talk about how does pi come into this?
Yeah.
All the way around is how far?
2 pi.
2 pi. Because we're talking about the unit circle here, right? Cool. And in degrees, all the way around is how much?
360.
360. So of course, 2 pi is the same thing as 360, which reduces to pi being the same thing as 180. Which only makes sense because if I want to go 180 degrees, that just is going to be half the circumference. That'll be pi. So pi is 180 degrees. You stop right there. Pi radians. Let me be very careful. Pi radians, not pi. Pi is freaking 3.14. But pi radians for a degree measure, it was the same distance that 180 degrees would. How we doing? So if you're facing this way and I said turn pi radians, you would just do a 180. Right? You would, I mean, it's the same thing. Cool.
So we can't do feet to radians, right?
The weird thing, the funny thing about radians is it's a unit that kind of gets out of the way. We're going to talk about that a little bit more when we really start to say, well, what if I don't have a radius of 1? What if I have some other radius? How does everything kind of come back together? Right? Everything we're talking about is a unit circle right now. So it kind of should make sense that what I'm going to do is I'm going to divide everything by r. I'm going to try to normalize it. If I divide it by r, it's kind of taking it back to 1. So that's going to come up here in a minute.
Okay.
Is it cool?
Yeah, we'll see in a minute.
Good. All right, we'll see in a minute when we get there. All right, so what you can do now is just like you know 1 foot is the same thing as 12 inches. Now we know pi radians is the same thing as 180 degrees, and we did a few of these yesterday. But just remember, if I had, what you got, Jeff? If I had 1.89 radians, I think I did exactly this yesterday. How many degrees would that be? Did I do 1.89?
Yeah, you did
It's
that.
one of my favorite numbers. I have no idea why. For the newbies, where would I put radians so that it would cancel on the top or the bottom?
On the bottom.
On the bottom. Flush there. So then radians cancels and degrees is there. So if you've had any chemistry in your life, you should look familiar. We're not. The good thing is we're not going to bring moles in. There's not going to be any Avogadro's number. None of that stuff. So some of you guys are upset, but too damn bad. Right? This is pure math. This is the real science. So what goes where?
180 on top.
Yeah, 180 degrees is the same thing as pi radians. And then you just plug it all in. Here I am going to go ahead and plug in, hit the pi button to get all the way down to decimal.
So what? 40.2. Do you want me to divide by pi?
Yes. Cool. I think we got 120, 108. Okay, maybe it's 108 point something or other.
29.
Because the last time we did 1.89 degrees.
Oh, I see. Cool.
So it was like
we're going the other way around.
2000.
All right. So that was remarkably quick. If you were not here yesterday, this is not going to be sufficient. You need to go watch the video or come see me, right, if you weren't here yesterday. Hopefully, if you were here yesterday, this is just reinforcing what we talked about. Yeah.
I know in the homework there was a question where it says you have a t of like 1.2. Where is the point that it gives you the 2 points?
Okay, all right. Which problem is that?
I have no idea.
So now we got to get into the question about reference angles and being more specific. So if you look at your... So let's do this. if I had, so T is the way they currently define. T is going to go away very quickly. T is the way they currently define what they call a terminal point. So if you walk around the circle and you stop, that's your terminal point.
So that's the x and y value, right?
Yes, that'll be the x and y value. So if I go around the unit circle 7 pi over 4 radians, right?
Yeah.
What will my reference angle, what they call it T bar? Is that true?
Yeah.
Yeah, this is another disagreement I have with. We're going to quickly kind of leave this behind. We're going to get into the true trig. This is not going to rule our life at all. It's just the idea, really, of finding a reference angle. So if I knew the angle I'm working with is 7 pi over 4, and you have the first quadrant values memorized like you're supposed to.
Well, we're working on it.
I don't mean you currently do. I said if you did, then you'd know how to solve this if you could find the reference angle. So if I'm at 7 pi over 4, where am I? Which quadrant am I in?
The third, fourth quadrant. Fourth one.
Beautiful, right? Because I'm how far away from 2 pi?
1
quarter.
A quarter of a pi away from 2 pi's, right? Which is not a bad place to be. So if I go around, here's 2 pi, right? All the way around is 2 pi. So here's 7 pi over 4. So the reference angle, the T bar they call it,
Pi over 4.
is going to be how far it is from the x-axis. What's the closest distance away from the x-axis? So not this distance, but that one.
Pi over 4.
Because like we talked about yesterday, if I know, I'm getting there, if I know the values for pi over 4, right, let me put it in here. And what are the values for pi over 4? We just looked at it.
Right, 2 over 2.
Right, 2 over 2. Right, 2 over 2. It's where they agree, of course, because it's right in the middle. If I know that, then of course this must be the same. Because if this is all about how big is the x and y piece, well, the x and y piece is going to be the same distance away on the other side. It's going to make the same triangle. Does that make sense?
Yeah.
That's the whole idea behind reference angles. If I know how far away from the x-axis to go this way, and I know what those values are because I've memorized them, all I got to do is figure out, well, how far away? It's the same distance away as that. That's the reference angle. So then the values must be the same except what's going to be negative.
The y.
Yeah, so down here the y is negative. I like it. So it'll be root 2 over 2, negative root 2 over 2. Yes, sir.
So another confusing thing in one of the questions I seen, it had an 8 on the bottom. So then the reference point, where would that be? Then?
Okay, same way. You can't find the values then, because pi over 8 is not something that we have to memorize. So we have to memorize basically 30, 60, 45, 0, 90, those kind of angles. You guys with me? That's exactly the angles that are on that sheet I gave you. Obviously, there are a ton more there's an infinite more values in between all those. You with me?
Yeah.
So I could do cosine of 11 pi over 17. I don't have to memorize it, but eventually we're going to actually, plug it in the calculator or figure out some other things we could do. Okay, cool. Maybe. So there are major values that we have to memorize because there's a lot of things you could do to, if you had like cosine of 22 and a half, or if I ask you what's the x piece, because that's what cosine is. If I ask you what's the x piece for 22 and a half degrees, well, how does that relate to an angle that we're supposed to know? What angle are we supposed to know that's kind of related to this?
Half 30.
It's half of
45.
45. So there actually is an identity I could use. It's called the half angle identity. Ooh. So if I knew what 45 degrees is, I would know what 22 and a half degrees is. I can build off of that. So that's why we want these 30, 45, 60 values. You want to memorize those because then you can build off of those for other things. Right?
So how does knowing the 22.5 degrees at cosine get you the x value?
This is in our future. All I'm asking you right now is how does that relate to something we're supposed to know? Isn't this half of 45, an angle we're supposed to know, right?
Yeah.
So in the future, we're going to learn an adjustment I can make that's called a half angle formula. So if I have a half of something that I'm supposed to know, I could actually do a little adjustment to that value. So that's in our future. I'm just trying to explain to you why we have to know these certain values. We have to know certain values to get things started. Sort of like memorizing your multiplication tables, which it seems like a lot of students aren't anymore, which really sucks.
Oh, they do it differently in school now.
For the world.
Yeah.
No, they demonize memorization entirely, which is really stupid. But oh, these examples.
So if you had pi over 8 and stuff like that, it would just be figuring out where it is in the quadrants.
Exactly. So if I had, for example, t equals 3 pi over 8. Now, what is that really close to?
Half.
Yes, you guys. Does everybody see that? It's really close to 4 pi over 8. It's below 4 pi over 8, right? 4 pi over 8 would be pi over 2. Where's pi over 2 on the picture?
90 degrees.
Yeah, it's at 90 degrees. It's here. So this is pi over 2. So at least I know where to draw this thing. This is 3 pi over 8. So if I ask you, if I have, so just to kind of set this up. So if I had t equals to, let's see, what do you got, Jeff? 5 pi over 8.
Wait.
Don't worry, this is the reference angle itself. I'm in the first quadrant, all right, guys? This is the first quadrant values. This is not really a question that they ask you. What's the reference angle for this? 3 pi over 8. I'm already there, right? It's like saying, what's the reference angle for pi over 4?
So that's the,
Pi over 4. I'm done.
so, okay, so the pi is the reference angle.
The 3 pi over 8 is going to be a reference. So if I'm at 5 pi over 8, where am I at? What
Just past
quadrant?
Second. Just past that.
Yeah, I'm over here, right? And how far away from a whole pi am I?
3.
Isn't that crazy? 3 pi over 8. There's a whole reason I did it. So if I knew this guy's values, it has to be exactly the same. So if this guy's values were A, B, does that freak anybody out? I don't know what they are, so I'm just call them A and B. Right. What would these values be?
Negative A and B.
Negative A, B. Right? It's in exactly the same place. The triangle I would draw would be the exact same triangle as the one here, just turned the other way. So all the side lengths would be the same. Right? So if I have the same angle, so this is 3 pi over 8, this is 3 pi over 8. The triangle that those both describe is exactly the same size. It's just that the base goes back. This is negative. That's why the x piece is negative. So that's the whole idea behind reference angles. It helps our memorization. It makes it so that we only have to memorize first quadrant values. Cool. Okay, maybe. Yeah.
For reference angles, don't you usually, if they give you a given number, you're supposed to go to the end of that quadrant and subtract it, and that's what...
No. It's always in relation to what?
The x-axis.
Reference angles are always in relation to the x-axis, period.
Oh.
Period. So if I'm at, let's say I'm at, what you got, Jeff? I don't know. 11 pi over 9. Right, why did I draw it there?
Because it's more than
It's in
More than 1.
In fact, how much more than 1 is it?
2.
So this reference angle would be 2 pi
Over 9.
over 9.
And then what's left will be 2 pi over 9.
Second, sorry. So this would be t. This would be the t that they give you. And then this would be the reference angle. Okay. Maybe. So it's really just a question of which quadrant is it in first. And then how much past or before the x-axis is it? That's the reference angle. That's how far away it is. Yeah.
So whenever it's in the first quadrant, it's always going to be the same number. So like that one, if it's 3 pi over 8, the reference angle is 3 pi over 8.
Yeah, if I know this value for 3 pi over 8, any angle that has a 3 pi over 8 reference angle has those same values. It's just that if I'm in a quadrant where the x-axis is negative, then that value would be negative. Here it would be both negative. Yeah. So let's do one we can actually do. Let's get away. They will have questions just for, can you find the reference angle, period. But to me, it's more interesting to get a reference angle for an angle that we're supposed to know. So let's kind of remind ourselves some of these values real quick. If I'm at pi over 6, somebody remember what the point is?
30. Oh, root 3 over 2.
And realize this. if I have a small angle, I'm close to the x-axis, right? If I'm close to the x-axis, the x piece is going to be a lot bigger. I haven't risen very much. The y piece is going to be much smaller. So if I'm at pi over 6, 30 degrees, the x part should be bigger. The y part should be smaller because I haven't risen very much yet. Yeah, root 3 over 2, 1/2. So at pi over 3, what will the values be?
1/2 over
1/2, root 3 over 2. Exactly. It's just a symmetric idea. Now I'm getting closer to the y-axis. So those are values you should know. And all I really desperately want you to understand that this is just the length of the base of the triangle. This is just the height of the triangle. So of course that point I end up at is this point. But it's much more important in a way to realize that the x piece and the y piece of the triangle is what that point captures. Right? And of course, why does that make sense? It's got to be on the unit circle. It's got to follow Pythagorean theorem. That's the whole reason we talked about that first. All these values have to fall in that Pythagorean theorem. Okay, so if I had, let's say I've got, what you got? Let's try some negative stuff out. What do you think negative?
Need to go the other
Yeah, just go the other way. You turn, instead of turning counterclockwise, you turn clockwise. So if I go negative 5 pi over 3, so that means I'm going this way. Do I go past this?
Yeah.
Yes. In fact, how far?
1.
In fact, think about it. Where am I almost? Yeah, so I'm going to go way the hell past this. This is almost negative 2 pi, which would be a complete revolution. All the way around would be negative 2 pi. So I want to go negative 5 pi over 3. So where did I end up? What's this reference angle?
1 pi over 3.
Yeah, how far away am I from the x-axis again? I'm pi over 3 away. Those two things happen together. How did I know where to draw it? Because I knew I was pi over 3 away from a complete revolution backwards. Therefore, I know what the reference angle is. I just said it to myself. Pi over 3 must be the reference angle. That's that leftover piece.
So what would be the reference number?
Pi over 3.
So right now, chapter 5 tries to actually talk about it like they're not angles yet, which is really annoying to me. But oh well. So they call this a reference number. I'm going to call it what the hell it is. It is a reference angle. They're talking about it, and I don't blame them that much, as if you're walking around the unit circle, which you are. But I want to get us away from the unit. It doesn't have to be the unit circle. It could be any circle. I still go through this many radians if I turn this much. I don't care how big the circle is. So it is a reference angle. They're going to call it a reference number. Let them do that. All right? But we realize what it really is. It's the radian measure of that term.
So the reference angle would be pi over 3?
Good. Reference angle.
Why would it be negative pi over 3?
Two reasons. My reference angle always has to be in the which quadrant?
First quadrant.
First quadrant. And negative pi over 3 would be in the fourth. Right? Plus, I don't care if I'm turning that way or this way. It's always the pure distance from the x-axis that I am, and that's always going to come out positive. So wherever I end up, I don't care how I got there. I just say, how far away am I from the x-axis? Right? I don't care if I'm walking backwards or forward. Is that cool? So it's a good question, though. But that negative just gets me to where I am, and then I don't care about how I got there. Just say, how far away am I from the x-axis? That's my reference number, or better, reference angle. Cool. So then what would the point be?
1/2.
Yeah, we already know what it's going to be, right?
1/2 root 3.
1/2 root 3 over 2. All right, that was kind of nice because it landed right on its own angle. So that was kind of nice. So what if I had t equal to, what you guys have? Negative 5 pi over 4. You guys try that one. Think about it in terms of how much did I go past something, or how much did I go past the x-axis? Don't say it out loud. Is it just barely over something? Is it just barely under something?
X and Y,
Yeah.
So, oh, I see truly this, okay.
Yeah.
But you actually want the inverse tangent there. These are, this would be the tangent of the angle, it would be sine or cosine. So you're trying to undo the tangent.
Find the angle.
Yes, to find the angle, you got to strip the tangent away so you get theta by itself.
Never mind.
So, negative 5 pi over 4 is just a little bit more than what special place?
Pi.
It's a little bit more than negative pi, right? And why do I care about that? I always want to relate it to 0 or pi or 2 pi, or you can even go past that, because you can imagine I could turn like 80 times and go insane.
Yeah, let's not do that.
Yeah, they do that sometimes. Maybe not 80. But you can quickly see it. If the fraction I give you itself is bigger than 2 pi, we'll do that next. We'll see if you can figure out what you would do. So if I go back, I'm definitely going to go back a full pi, and then how much more?
Pi 4.
A quarter. So I know that this reference angle is got to be...
Root 2 over 2 over 2 over 2.
Well, the reference angle is pi over 4. You with me? Why is it that?
It's that much farther.
It's that much farther. That's how much I went past the x-axis. So as I say that to myself, just so I can draw the line in the right place, I'm actually telling myself the answer for the reference number or reference angle. Because that must be how far away from the x-axis I went. So if I go back a full pi, how far do I still have to go? Pi over 4.
Yeah.
So that must be the reference angle. Isn't that how far away from the x-axis I am? All right, good, good. I mean, those two ideas are the same. Yeah.
Why don't you go how far away you are from the x-axis going, continue going? Why'd you go?
Because again, one purpose for reference angles is so I only have to memorize first quadrant values.
Okay.
If I do this, then that's a second quadrant value. I don't know if you guys see what I'm saying.
Yeah.
This is a first quadrant value, definitely. The value here would be in the second quadrant, right? So it's not as useful. I don't want to memorize the second quadrant values. Cool. So what, in general, for pi over 4 reference angle, it's going to be what values?
Square root 2 over 2.
Yeah, well, in general, it's root 2 over 2, root 2 over 2.
Yeah.
So here, which one's going to be negative?
X.
The x value.
Okay, so so pi over 4 is the reference angle and the reference number,
Yes.
and then the negative root 2 over 2, root 2 over 2, that's just the point.
That's the terminal point.
That's the terminal
That's the point. You stop at on the circle.
Okay,
So if I
that will
turn
always
by
be the
this
terminal point?
much, if I turn by that much, I stop at that point.
And that is always going to be your terminal point? Is it gonna be
Yes.
written in
For that will always be the terminal point. If I turn by that much, I will always stop at that point.
Okay.
I must. Good.
On the unit circle.
On the unit circle. And we'll see later that everything else is just multiples of this. So they all reduce to this anyway.
So if you do 4 pi.
Okay. So, let's try what I said earlier. If I had this, let's see. What's it? Let's do
9 pi. Or 60.
So what do you think you should do here? I mean, what's obvious about this that I've drawn up here? It's how many revolutions does it? I mean, you may not know how many, but it's definitely more than one turn, isn't it?
Yeah.
Because one turn would have been 6 pi over 3, right? That would have been a full 2 pi.
Yeah.
Another turn would be 12 pi over 3. You with me? So how much past that have I gone?
1.
So let's try this again. You ready? So here's what you do when you're given a number that's obviously more than one turn. And how do I know it's more than one turn here? Because it's more than 2 pi. That is definitely more than 2 pi. So I start by, if I'm not sure how many more than 2 pi it is, I subtract 2 pi. So if I turn 5 times, I won't, and I end up facing here. You with me? If I take one turn away, I'm still facing here, am I not? So if I could subtract and add terms all frickin' day long, we could have done that here, to be honest. I could have added 2 pi to this. Let's see what we get if we do that. See if you guys can stay with me. If I add 2 pi to this, it's 8 pi over 4. Minus 5 pi over 4 is
3 pi.
3 pi over 4, and that's maybe a little bit easier to see that it's there. Isn't that pi over 4 away from a full pi?
Yes.
Am I not in the same place whichever way I look at the damn thing, right? So if I add or subtract a full term, I'm not changing where I am. And this is where you guys are kind of going a little crazy. But that's one useful feature later. Right now, it's kind of like in our way. I got to subtract a few terms. But later, if I want to have like a spring that coils up, you guys kind of get me? And a circle defines it. So I could actually have trig functions, and thankfully they repeat themselves. So I have one part of the function said, go up, keep going up. And the other one just says, keep drawing a circle. Just keep drawing a circle. So it doesn't draw over itself. Why not? Because I have another part saying, keep going up, keep going up. So the fact that it repeats values is actually useful. Right now, it's sort of annoying. There's more than one term in there. Let me take some out of the way. So if I subtract 2 pi, right, which is 6 pi over 3, what do I get?
10 pi over 3.
Which is still more than, so let me subtract another 2 pi.
4 pi over 3.
Yeah, so 4 pi over 3. So where am I then?
Third quadrant.
Third quadrant, I love it because I'm a little bit past
Fourth pi.
pi. So if I go a pi, this is pi. How much past pi would I go?
1/3.
So that tells me my reference angle. So because that's how much past pi I went. Pi is the x-axis. Pi defines the x-axis. If you're right. I don't know. You know. Okay. What part's not good?
No, I think I'm good.
You're good.
It just depends on what you say next.
I like it.
And then I'll know if I'm following the bouncing ball.
Alright, so now, what values would this have then? What pi over 3 in general has the values 1/2 root 3 over 2.
It's going to be negative 1/2, negative root
Yeah,
3
they're
over
both going to be negative now because I'm in the quadrant where they're both negative. Cool, I like it. So let me do this for you guys. You got to get these basics down. But let me do a little bit of something for you. We're working to the point where we can figure out some problem like this. We're nowhere near the point we can do this. I just want to show you what this all is leading up to. So if I was standing here, yay, and I know this thing is way off in the distance, I see this tall thing. I know that it's 60 feet tall. You with me? I know that thing is 60 feet tall, and I want to get there. I'm tired. I've been walking all day. I'm like, how much freaking further? So I want to know how far away am I from there. If I can figure out the angle, I don't know if you've ever seen these things. I'm going to see if I can get a hold of one of these things. If you can figure out the angle that you look through to get to the top. So if I can figure out, so if I lay on the ground, actually, yay. And I look up here and I see the angle. I'm just ahead. I buried myself. I went a little too far. If I can see the angle that is to the top, I can use trig. I can use what we're learning right now to figure out how long this is. All I need to know is the angle that it takes to get to the top and how tall this thing is. So if I have a known height on something far off in the distance, I can actually figure out how far away I am if I just know the angle it takes to look up to the top. It's because the closer it is, the larger the angle is going to be, isn't it? Mm-hmm. And the further away it is, the shorter. So there's a direct relationship between this angle and how close it is. And that relationship mathematically is trig. So that's the direction we're heading. Right? And maybe by the end of today, we'll actually be able to do this problem. We'll see. It all depends.
And that's dealing with sines and cosines.
Yes, and even maybe some tangents. Right?
Yay!
Yay! And the crowd went semi-something. All right.
And the crowd groans.
Yeah, repeatedly. Okay, cool. There's this one little thing that comes right off of what we just did. This is kind of another silly thing. If I'm at pi over 5, which is obviously not something you guys have to know. And that's not drawn to scale. Another way to define that angle, pi over 5 tells me I go this way. If I wanted to say, well, how far would I have to go this way? Can you figure that out?
Negative 4 over 5 pi. Negative 4 over 5 pi. Or negative 4 pi over 5.
The whole thing, though, is how many pi's?
It's
Two.
One.
2. So you gotta be careful. The whole thing is 2 pi, isn't it? You get all the way around, it's 2 pi.
Negative 9 pi.
Yeah, because 2 pi is 10 pi over 5. So I'd have to go back 9 pi over 5. Good. So another name for that angle is negative 9 pi over 5. These are what's called coterminal. I love the language. It sounds like they both died. So coterminal angles.
Yeah,
Exactly. They move and then they stop. How many coterminal angles are there for any given angle?
One.
Infinite amount. I could turn once, I could turn twice. I could turn backwards 78 times. I could turn forwards 528 million times. You guys kind of with me. And I'm hoping, I hope, keep that idea in mind about the fact that it repeats values is useful, kind of, if I can get it out of its own way. Otherwise, it's just kind of spinning around forever over top of itself.
I need to see this together.
Say again?
I need to see it together.
See what?
Sure.
The circle's going up.
Oh yeah.
Oh, yeah, okay. Okay, I could probably find that. It's kind of nifty. It's something you do in Calc 3.
A little bit ahead of us.
Well, not even that. I'm thinking about too much. You could actually do it in pre-calc, but I don't think we're going to get to three-dimensional stuff yet.
So the coterminal angles is the opposite of.
I don't want to. Now be careful. It has nothing to do with reference angle, right? But the idea of coterminal just means there's a lot of different ways to get to point this way. If I'm pointing this way first, I could just go like that and I'm pointing that way. Or I could have went like that and I'm pointed that way, right? So there's a lot of different ways to end up pointing that way. That's all coterminal angles mean. So I could turn a little bit and I'm done. Or I could turn back and I'm done. Or I could turn all the way around once and then stop there and I'm done. So that would be another. What would that one be? The black line here, what would that coterminal angle be? How do I get that?
11 over 5?
Yeah, exactly. Because what would it be? It'd be a full turn, which is 2 pi,
And then another
which is
one.
10 pi over 5, plus pi over 5, so that would be 11 pi over 5. That's a full turn plus a little bit extra. Okay, so this math, just playing with the values, you just got to get a little used to it, but the math itself should be very simple. This is very simple mathematics. It's just inside of something we're not used to. Okay, maybe. All right. Oh, we got it there. More motivation. So, two other little tiny things. This is in section 6.1, if you're curious. 6.1 talks about arc length, and it talks about area of a sector. Oh yeah. So arc length would be, if I have a circle of radius r, and I go through this much, let's say this much. Why not? I want to know how long is that, right? So let's see. Let's do a concrete example of this, and then we'll try to figure out what the general formula would be. Right? So if I had a circle, circumference, let's say the radius is 8. So what would the circumference be? 16 pi. Good. Is everybody with me? All right. And I want to know if I go here, let's say this is 2 pi over 3. This angle here is 2 pi over 3. I want to know how far I would go on the circle itself. If it was a unit circle, I would go 2 pi over 3. Because that's the real measure of a unit circle. This is not a unit circle. So I want to know how far would I actually go. Yes, sir?
2 pi over 3 times the radius?
Not quite.
2 pi over 3.
Well, I mean, we're going to get there, but how do you get there?
Write it down.
How far, if I went all the way around, I'd be at 16 pi, right?
Yeah.
If I went halfway around, I'd be at 8 pi. So if I could just figure out what percentage of the circle I've gone, I can figure out how long this is. Isn't that what I just said? If I go all the way, 100%, that's 16 pi. If I go halfway, 1/2 of 16 pi is 8 pi. So if I knew what fraction of the whole thing this was, well, how many radians is the whole thing? 2 pi. So if I say, okay, 2 pi over 3, what fraction is that of 2 pi? I want to see what fraction of the whole thing have I gone. And actually, you can kind of see already, I mean, how far around have I gone? What is 2 pi over 3 divided by 2 pi?
2 pi.
Don't overthink it. What's 2 pi over 1 divided by 2 pi? What's 2 pi divided by 2 pi? 1. So 2 pi over 3 divided by 2 pi is 1/3. All right, the 2 pi's cancel. Yes. So 8/3 divided by 8 is 1/3. Let it be that easy, please. So I've gone 1/3 of the way around the circle. So how far have I gone then in terms of the circumference?
1/3 of 16.
1/3 of 16 pi. That's how far I've gone. So in general, if I take, what we just did was I took the angle that I actually went through, divided by the total angle that's in the circle. You just stop right there. Is that cool? That's what we just did. But I just want to figure out what fraction of the circle have I gone through. So if I take the angle I went through, divided by the whole thing, that's the fraction of it that I've gone. And I multiply that by
This circumference.
circumference, which in general is 2 pi r, even better. So this would be what I call my arc length. And arc length, we give it the letter S. Of course. So what happens there? I mean, how does that reduce down? The 2 pi's cancel, so you just get a really nice little S equals r thing. I just know to put the r first. So that is the measure of the arc for any circle. So I want you to realize something kind of interesting. For a unit circle, if I went 2 pi over 3, how far did I go? If I went through a radian of 2 pi over 3 angle, for a unit circle, how far did I go? 2 pi over 3. That's how we introduced radians, right? That's the actual measure on the unit circle, how far I go. So all r does is it's a multiplier. If I'm on a circle that's twice as big, the r is 2, I'm going to go twice as far. It would be 2 times what I normally would go. So that's really all. That's a good job. It's r times theta. It's a multiplier. Right? So normally I would just go that many radians. But now I multiply by the radius to see, well, for the bigger circle, how far am I going to go? Or for a smaller circle, it would be half as much or something like that. How are we doing so far? All right. Now the area of a certain sector is going to be a little bit easier because we've actually already got a huge thing right there that we need. What's the area of a whole circle? Yeah, why is it pi r squared?
He said it was.
Really, really quickly. Let me see if you guys can go with me on this. So what? Let me try again. Follow me along. Here we go. I'm not going to make that a question. If you took a circle, I don't know if you guys have ever seen this, and you cut to the edge. You cut to the edge like that. But you don't cut through the edge. So you can actually pick it up and open it. Are you guys kind of with me?
Yeah.
So I cut out from the center, cut down the middle, cut out from the center. I can lay it out like this.
Oh, yeah.
Now how long is this? Let's see here. How long is that?
R.
R. Beautiful. And how long is this?
D.
Pi.
R squared.
Circumference. Half the circumference of pi.
So pi r. Good.
Okay.
Right? All the way around is 2 pi r, so that length is pi r. You with me? So do the same thing with the bottom. Fit it in. What's the area of that rectangle? Beautiful. So there you go. Pi r squared. So the area of a circle, someday I'll actually bring construction big. Is pi r squared. Yes, sir.
How did you make the rounded edges flat?
You take the limit as your number of cuts goes to infinity. And then the more and more you do, the flatter it gets. So at the limit of infinity, it'll be exactly flat. It's a really good question. You notice how I try to go past that. But that's the answer.
Could we kind of go back to that one and finish it off?
Yeah.
What happened here?
Oh,
Oh,
SRO and
No.
I mean,
I don't understand. So here's the equation.
right.
For this, what will it be? The arc length here would be 16 pi over 3. And if you wanted to make that, if you know this is 8 feet, that would be that many feet. Right? You wouldn't tell somebody, oh, just walk 16 pi over 3 feet. You could turn that into a decimal there, right? Okay. Is that cool? So we basically had the work here. I just wanted to do a concrete example and then analyze what we did and make a general formula out of it.
Okay, but what about for the general formula for theta? Wouldn't that be the degree? Or 2?
So theta is going to be a given thing. It's going to be a known thing. So I'm going to ask you, what would the arc length be if you walked through this many radians of an angle measure? So they would have to tell you. So another example, if I had somebody who walked through, what you gotcha? Oh, let's say 5 pi over 3 radians. And the radius of this is 20. If they walk through 5 pi over 3, how long is that? All we got to do now is use the formula. What's the radius? 20. What's the angle measure in radians? This has got to be in radians. It's got to be the real. This never would work for degrees. Degrees completely made up. 20 times 5 pi over 3. So it'd be 100 pi over 3. That's how far I would walk. A little over 100, right? Because pi and 3 almost reduced to 1. Just about. So if that was feet, I would walk a little over 100 feet to get there. Okay, cool. All right. So for the area of a sector, now, a sector really is just this. So I'm just going to find the area that has in it. Right? So it's really related to the arc length. So the nice thing about this, we're going to prove it very carefully, and then I'm going to show you a shortcut as to why it is what it is. So what's the area of a circle when you got that pi r squared? So the whole area of a circle is pi r squared. So let's just do the same angle again. If I went through an angle of 2 pi over 3, what fractional part of the circle have I cut out? If I cut that much out?
2 pi over 3 over 2.
Exactly, 2 pi over 3 over 2. This whole theta over 2 pi thing is going to happen again. So I would have cut out 2 pi over 3 over 2 pi. That fraction of the whole thing, and what would the whole thing be here? Let's make this 8 again. What's the area of this circle? 64 pi. Cool. So I would have gone through 1/3. I would have cut 1/3 of the circle out, and the circle's got 64 pi of an area. So with 1/3 of 64 pi, so 64 pi over 3, and then you can make that into decimal if you want to. Right? Make it a little more something that humans understand.
What does that say?
64.
After the 1/3.
64.
64 pi.
It's the area
Oh,
of the
okay.
circle.
Cool. Okay. So what we just did was, we did the same thing about theta over 2 pi there. I'm hoping that makes sense. If I just know the fraction of the circle I've turned through, I take that fraction of the circumference or the area, and that's how much area or circumference I've actually captured. I mean, that is half of the circle, I would have gone half the area. So just got to figure out how far through the circle have I gone through. That fractional piece, that's huge. So in general, this would be, the area of the sector would be theta over 2 pi, like we had here, times the area of the circle. What's that in general? Pi r squared. So you get area equals 1/2 theta. Let me write it the way I normally do. R squared theta. So that's the area of the sector. Let me show you a quick little neat way to get that a different way.
Are they always going to give us the...
They have to give us something. They have to, and how many unknowns are there in that equation?
Well, if we start with
3. A, R, and theta. So they have to give me 2 of those things. They could have said, if there's an area of 11 and the radius of the circle is 2, then what angle did I go through? We just plug in the values and solve. So the uses of these things are nice. Let them be nice. The idea of where they came from, we had to go through a little bit, but hopefully they make sense. And again, it's almost too simple of an idea. If I know the whole damn circle is 2 pi, or whatever, in this case it was 16 pi circumference. If I went through half the circle, I would have walked 8 pi, correct? So if I could just figure out what fraction of the whole thing did I go through, I take that fraction of 16 pi. That's exactly what this formula says. That's the fraction of the whole degrees, or radians, that I went through, times what the whole thing is the actual part that I went through. Same idea for area. Exactly the same idea for area. And here's a really cool thing. So you guys can see this. So this is R. This is that little piece of a circle. This is a sector out of a circle. How long is this? This is the arc length. So let me give you this. This is theta.
Radius time.
Yeah, R theta. You with me? So doesn't it look almost like a triangle? Just with a curvy bottom?
Yeah.
And what's the area of a triangle? Isn't it 1/2 base times height? I love that this works. It's really got a little bit to do with the limiting factors of making this less curvy, but 1/2, what's the base? I know it's curved, but the base is R theta, isn't it?
Mm-hmm.
And what's the height?
R.
R, and don't you get 1/2 R squared theta?
Yeah.
Same damn thing, right? It's not good enough proof, but it's interesting that it actually follows the same rule, even though it's a curvy triangle. And it's kind of cool. Marisa knows what to say to make me feel better. All right. But yeah, Jeff, that is cool. All right, so I definitely want to get.
Could you go through this bottom portion for me one more time, please?
All right, so if I go 2 pi over 3, this is exactly what we did earlier.
I got that.
1/3 of the whole circle. The whole circle has how much area?
2 pi.
64 pi area.
Sorry.
So 1/3 of that must be what I caught. End.
Okay.
Good. I definitely want to not let you out of here until I talk about this last thing. It's too bad. 6.2.
Jumping back and forth.
It might be a good idea to have your homework timeline sheet out next to you so you don't freak out, because we are going to be going from 6 to 5 to 6 to 5. Right? Mm-hmm. And just, either trust me or don't, but you just do it like that. They have the same ideas, just from 2 different perspectives.
So we've done 5-1 and 6-1.
Yes.
And now we're doing 6-2.
Yes. Cool.
Okay.
Last little thing today. And again, we're going to continuously kind of go over what we've already done a little bit. So don't feel like you have to get everything the first time I talk about it. That's insane. So it's going to take a little while for this to sink in. Trigonometry is probably new to most of you guys. Right? You guys have never had any trig before. So, okay, in high school you might have had like a semester's worth of trig or something.
I know the geometry they teach here, they get a little bit into trigonometry.
A little bit.
Mine was
Okay.
mixed in.
What's that?
Mine was mixed in for like all my classes.
Oh, I like that even better, because you can with trig you can do that. It shows up everywhere, and once you learn it, it's in everything you do after that almost. So the last thing I want to do is if I step out of the unit circles. Here it is for the last time here. Not the last time we're going to do it. If I take that triangle out of there and just look at it by itself, so I know that's a right triangle if I could draw. I know that, okay, so this is the x piece, the y piece, and this is the radius. So here's what ends up happening for, let's do a specific example. Let's say theta is pi over 3. We've been working with that a lot today. So let's say that theta is pi over 3. How would I label these sides then? What would these sides be? For pi over 3, what's the x piece for pi over 3? What's the terminal point for pi over 3?
What happened?
Yeah, 1/2. So this would be 1/2 here. What's the y piece got to be?
Root 3 over 2.
Okay. And just to check, if you square those and add them, of course you get 1. That's where they came from. So that has to be true. So this would be 1. Now, if I made a triangle that was twice as big, all right? I'm not going to draw it to scale, but just pretend like this is not to scale. If I double the side lengths of these things, what would all the side lengths be? This would be, if I doubled all the sides, this would be root 3. This would become 1,
2.
and this would become 2. Now, what I'm about to say, that I could have tripled them, I could have times them by 8, I could have cut them in half. Everything I'm about to say would be the same. Any multiple I choose to use. Here's why trig works. Let's start with cosine, because it's the only one I've really talked a little bit about. Cosine is the one that talks about which side. X. And cosine is defined to be the x side divided by the radius. I will bring in SOHCAHTOA later, but I want to teach you the right way first. And then we'll bring in SOHCAHTOA in case you know it, just so that everybody can see where it comes from, what the hell it is. So for both of these, what we cosine, so cosine of pi over 3. What is the cosine of pi over 3 then? Working with the triangle here.
1/2 over 1.
Yeah, it would be 1/2 over 1 here, so it would be 1/2, which makes sense because I introduced cosine as the x piece of the point, and the point here would be 1/2 comma root 3 over 2. That's the x piece of the point. Now what's cosine over here? Everybody cool with the fact that that's the same exact angle? If I just double the size of the triangle, angles don't care. That angle is the same as that angle, it's the same as that angle, right? I didn't make the angle get bigger. So of course the angle is the exact same, but what's really cool is this would be 1 over 2, which is still 1/2. No matter what multiple you used, of course, it would cancel out when you made the ratio. You guys got it with me? That's why, looking backwards now, we can talk about the unit circle and learn everything about the unit circle, because if it's a bigger freaking circle, we divide by the radius. We bring everything back to its most lowest terms. So everything is actually related to the same values. So I don't care if your triangle is as big as the freaking universe. If I have a pi over 3 angle in that dude, then the ratio of x to r is going to be 1/2, period.
Repeat that one. If you have... Okay, I got it.
All right. So, if you understand that, you understand all the trig functions. You just have to be told what they are. Right? So, cosine theta captures the x value. And let me put this little caveat in there. As long as the angle we're talking about is in the base. If I was talking about that angle, what could I do?
Just change.
Just turn the triangle, right? That's the one advantage that SOHCAHTOA has. SOHCAHTOA can do a triangle no matter how it's sitting. That's the one advantage it has versus 80 billion that this has. Yeah.
Would sine be pi piece over r?
Yeah, I love it. Kick ass. Look at you. So sine theta, so cosine theta is x over r. Sine theta is y over r. So cosine is going to be biggest when it's closer to the x-axis, because cosine likes x. Cosine actually talks about how big the x piece is. Sine is going to be biggest when it's closer to the y-axis. That's why sine is the absolute biggest when I'm at 90 degrees. Because when I'm at 90, it's all freaking y. There's no x, right? Cosine is biggest when I'm at 0 degrees. Because then it's all x. Now at 180 degrees, what's happening?
Same thing, cosine.
Except cosine there would be
smaller.
Negative 1. You with me?
Yeah.
Because then what would the x? Here it's positive 1. At 0 degrees, at 180 degrees, it would be negative 1.
So it's smaller.
So we already know a few values for cosine. Cosine of 0 is 1. Cosine of 180 degrees, or cosine of pi, they're both the same thing, right? Is negative 1. So this is really why you're going to memorize those points. And if you'd rather, you could just memorize cosine 30, cosine 60, cosine 45, cosine pi over 6, right? Radians and degrees. If you don't want to memorize the points, because what's more important is that you know what sine of 60 is quickly. If you try to type in your calculator and I see 0.7 or whatever crap decimals, no. If it's a value you're supposed to know, I better not see any freaking decimals, right? I better see rad 3 over 2 or rad 2 over 2 or so forth. And finally, here's a new dude. Tangent theta. He'll be y over x. So another way to define tangent is sine over cosine. Because what happens if I do sine theta over cosine theta? That would be y over r over x over r, and of course the r's cancel. So you get y over x. Good. So tangent theta, we call that sine theta over cosine theta. So what would the tangent of 30 degrees be? How do you think you piece that together? Tangent 30 would be what? Would be sine 30 over cosine 30. Now what's sine of 30 degrees? Now the way I think about it, that's close to the x-axis. Sine should be small. It must be the 1/2 value. I like it. No, Jeff, 1/2. Cosine 30, opposite reasoning, it's close to the x-axis, should be big. So what's that going to be? Rad 3 over 2. You guys kind of see, that's how I think about it. I don't actually have it memorized. I just think if it's close to the x-axis, sine is small, cosine's big. If it's right in the middle, they're rad 2 over 2, they're the same. So yeah, the over 2's cancel, you get 1 over rad 3, which is rad 3 over 3. So to keep with the promise I made to myself, I didn't really make it to you guys. I do want to do this problem real quick. All right, we got that far. There are 3 more of these. Oh yeah. The funny thing is they're just these flips. Okay. So those are the reciprocal trigonometric functions. It's just flipping the damn little 3 dudes that we have. This really covers everything. These 2 actually cover almost everything by themselves. This is the last possible ratio you can really make. And the other 3 are just, you could turn them around. So I really want to show you a nice concrete example of trig helping us figure something out. So if I'm here, I'm laying on the ground, I'm looking at this big tall thing, I'm like, how far do I have to go? And I know this is 30 degrees. I know this is 60 feet. And I don't know how far I've got to go. What trig function relates those sides? Careful. Tangent. I don't know anything about the hypotenuse, and I don't care. But I know y and x. So the tangent of 30 degrees must equal what from this triangle? 60, the y piece, over x, the x piece. Right? What is tangent of 30 degrees? We just figured the damn thing out, right? And this is independent of how large your triangle is. It's the beauty of this. The minute I set that ratio up, they would reduce to this. So that I can solve for what x is. So tangent 30 is rad 3 over 3. How do I figure out what x is? Let's put this in here. Let's make this 1 over rad 3. You can maybe choose y. X equals rad 3 times 60.
Which is whatever it says.
Which is whatever it is, yeah. Let's see anybody help me out. Well, I want to know this damn problem that I made out of nowhere. I want to know what the answer is. $103 point blah blah. So I know I'd have 103 something feet left to go, right? Or if this was some kind of a mountain, 60,000 feet or something. I know I have 103,000 feet left to go.
So next time we bury ourselves.
What's that?
So
If you,
next
yeah,
time we
exactly. Bury yourself.
Tree, we got it.
Yeah. So again, that last thing especially was just me throwing it in there. We're going to definitely do a lot more of this in the future, but I'm going to firm this up next time.
Okay, so I'm trying to figure out the shortcut for this 16 over 3. It obviously comes down.